Hello and welcome back. Enrichment, integration, hard, definite integral. It's actually accessible by straight mathematicians. It's no more than straight maths involved in that. However, it is a 5-star question. And before I show you how to do this particular one, I'm going to just tell you a little bit about this particular integral because I was looking on YouTube and Professor Penn done this integral only a few days ago, so I thought, well, quite interesting. And I paused the video because I want to do it myself, obviously. And I did do the integral, of course, but I done it in a completely different way when I watched the video afterwards by Professor Penn. I thought maybe I'll steal this question, put it in one of my books or one of my papers. But before I do that, let me just check my own resources because I've got so much stuff that I've written over the years that I cannot possibly remember what I've got and what I haven't got. And to my surprise, I had already the very same integral. It's appearing on my special paper, SP Paper V, which was done around 2015, I think I wrote these papers. So it's been with me for a very long time, and to my surprise, further to my surprise, I showed two methods for that particular integral, and these two methods are different to what I want to show you today and different to what Professor Penn did on his own video. Okay, let's not waste any more time. This is the newest version. You have two more versions, of course, if you go to that particular paper that I just mentioned. But I'm going to do a little bit of a talk and an analysis for this particular integral and what's going through my head when I look at something like this. This denominator is very, very special. The things that go to my head when I see the 16 sine 2x is not the 16. It's like, let's look at this sine of 2x. And some numbers at the front, could be 9, could be anything, doesn't really matter. This is the same as 2 sine x cos x. And if I have some numbers, for example, a 1. Why 1? Because I don't have a 1, I have a 9 in there. It doesn't really matter what I have in there because I can borrow just the 1. Of course, this one on the other side, I can write it as cos squared x plus sine squared x, which of course this is a perfect expansion of the cos of x plus the sine of x. I think I've done actually another integral very recently. I can't quite remember what was the integral that had similar ideas. I can't think at the moment, but a similar kind of pattern developed on that particular one. So that is that. Now, is that good because I got the sine x plus cos x on the numerator for this particular one? The answer, believe it or not, is no. I want something different, not so much different than what I've got here, in order to match my numerator. If you look at I'm looking at the interior of this bracket, the cos x plus sine x, and I look at what cos differentiates to and what sine differentiates to, and I look on my numerator now. Cos differentiates to minus sine, and sine differentiates to plus cos. I want to use some kind of substitution, but at the moment I've got a problem with my signs. Okay, but suppose I had it the other way around. Suppose I had not just swapping the sine and the cos. Suppose I had the sine of x minus the cos of x. And now look what happens when I check the differentials. The sine differentiates to plus cos and the minus cos differentiates to plus sine. That will give me scope for substitution. How does that change things here on what I want up there? Well, quite clearly this will still be positives. It doesn't matter if I expand it, but I need the minus in here. So somehow, forget about this bit here now. When I look at this denominator, I have the wrong sign on the term that has 16 sine 2x. I would dearly like to have a minus in there. I'm going to put all these kind of things. I'm not going a little bit too fast, otherwise the video is going to go very, very long. But I'm trying to give you a little bit of, try to understand what's going through my head as I'm looking at this integral and the motivation behind all of this. Because of course, you have to see a few steps ahead in order to come up with a sensible plan. So I'm going to put the plan in action. The first thing, I need the minus on this term here. How am I going to create a minus in there? There's two ways. Either stick a minus at the front And of course, this will change minus 9 and minus 16 because that's where I want it. This will also be useful if you don't have limits, I guess. But here, because I have limits, okay, probably better would be to actually swap the limits to pi over 4 at the bottom and 0 on the top. That will generate, of course, a minus. And of course, the minus I can put either on the top or at the bottom, and it suits me to put it at the bottom. So that's step number 1. Let's pause for breath. And let's think what we're going to do next. I'm already making stupid things. Minus 16, sine of 2x, dx. Okay. Probably want to come out of the integral and manipulate this expression here to what I actually need. So let's make some, let's clear this board. And let's concentrate on this denominator. Minus 9 minus 32, double angle of course, sine x cos x. I want to create the perfect square, and my target is to create sine x minus cos x all squared. So in order to do that, I need, of course, to add to this particular quantity a 16 sine squared x plus 16 cos squared x. If you look at including the minus here, okay, if I factorize the 16 on the outside, so it'll be like this basically. Okay, this will create this bit here. If you look at it, sine squared, 16 sine squared, plus 16 cos squared, minus 2 lots of that, times 16 is 32. So this is what I've got on my denominator at the moment, up to here. I added 16 sine squared plus 16 cos squared x, which of course, I need to subtract it, but I don't subtract all of this. Of course, this is equal to 1, so I'm going to subtract 16. So this is my denominator, and I haven't changed anything. Make sure you follow what I'm doing and you're happy with what I've done so far. Then, of course, the minus 16 and the minus 9, I can write it as minus 25. This is that and that put together. And this I'm going to factorize on the outside, a plus 16 out of those 3 terms, and I'm going to write this as sine squared x minus 2 sine x cos x plus the cos squared of x. So far so good. Just checking we haven't made any mistakes. I'm the king of mistakes, so please watch it and just make sure you're happy with what I've done so far. And of course, this is now on my next line. Let me just write this first. It's going to be 16, this is the perfect square, sine of x minus the cos of x all squared, and the minus 25 is, I wrote it on the right. Okay, what has happened just now? I'm just going to leave that in there. This denominator is exactly the same thing. And if you go back to a few minutes ago, what I was saying, what I'm trying to create now is something that differentiates to this numerator. Look at it, sine differentiates to plus cos, and minus cos differentiates to plus sine. So my intention is, once I rewrite my denominator, is to use a substitution. So equal, and we're having now pi over 4 at the bottom, 0 on the top, numerator untouched, and denominator now has been changed to this quantity. 16, I'm going to move my hand out of the way in a second, minus cos x all squared minus 25 dx. Okay, I'm going to use a substitution so we can all see what's going on in there. Let's put the workings up here. U is sine x minus cos x, that's my denominator there. I'm going to leave it in differential form because it's easier. Du is equal to cos x plus sine x in a bracket dx. And the reason I'm leaving it like that, because if you look at what I've got up there and compare with my substitution, that is the bit that I have here. So I can replace this with the u, and this of course will be my u, or u squared, so let's say because it's squared. Okay, I need to change the limits, so let's convert these limits as well. I've got 0 for my x. When x is equal to 0, that goes 0, cos of 0 is now a 1, so we're gonna go to minus 1. And when we're putting pi over 4, both the sine and the cos of pi over 4, they're exactly the same, and therefore they will cancel out. Okay, let's put our things into this integral and see what happens. The pi over 4 will go to 0, the 0 will go to negative 1. All of this is my du, and my denominator will change to 16 u squared minus 25. I was about to write du there stupidly. I'm going to do some partial fractions. I don't remember by heart the standard. There are standard results for integration. I'll normally derive what I need, and I'll go for partial fractions. It doesn't take that long. So this is of course a difference of squares. 0 and minus 1. I will not need this one unless I made a mistake and to check. It's too late now to check for mistakes. We have gone too far, so I will rub it off, and I will factorize this to 4u minus 5, 4u plus 5, 1 du. I'm going to do this by cover up or inspection. So let's copy the limits first of all. 0 and minus 1, and prepare two fractions. One will be out of 4u minus 5. The other one will be 4u plus 5. Okay, so when we're putting in there u is equal to 5 quarters for this, we're going to get 1 over 5 quarters is 10. So I'm going to get 1/10. Just double checking, 5 quarters is a 10th. So the number in front of the 4u minus 5 is a 10th, and purely from experience, I think that's got to be a minus a 10th to cancel the 4 u's. I just want to check it. So I didn't do any calculation for that. We got 4/10 of u minus 4/10 of u cancel, and I've got half minus half, which is the 1. So this is correct, du. Okay, partial fractions are done. I'm going to integrate this now with a given limit. So I've got 1/10, make it 1/40th, log of 4u minus 5, and then we're having minus 1/40th again, the log of 4u plus 5 between 0 and minus 1, and probably better to write it as let's go all the way to the end. I'm going to compact the logs, write 1/40th, and I'm going to move it outside the evaluation limits, the 1/40th, and I'm going to have inside the log mod 4u minus 5 over 4u plus 5, and I have the limits between what is my u now? My u is going to be minus 1, and for you putting u is equal to 0. Sorry, I put minus 1 and 0, which is, sorry, 1/40th, and I'm going to get the log of, when I put minus 1 in there, I'm going to get on the top minus 1 minus 5, which is minus 9, and on the bottom, when this is 0, sorry, we're still on minus 1. What am I saying? Stupid things I'm saying. Sorry, I do apologize. I'm still on the denominator with the limit of minus 1. Minus 1, so I'll go a 1, and then I go minus 1/40th Okay, I'm putting 0 now on both top and bottom. I'm going to get the log of minus 5 on the top and 5 at the bottom. Okay, of course this will give me, I can squeeze it perhaps on the side here, 1/40th. First of all, the mod of minus 5 over 5 is 1. Log of 1 is, of course, 0. So there's nothing from this. It's just this bit here. Log of mod of minus 9 is the log of 9. So the final answer is 1/40th log of 9, which I personally would have written as 1/20th log 3. And that's the end of the integral, and I hope you followed my method. As I said, it's completely different to what are the two methods. I'm actually showing two methods in my paper, and Professor Penn uses a variant of that, but very long-winded, and I thought to myself, why is that necessary? This is the way, obviously, that I think about it. All straight maths, no further maths in this particular one. I hope you enjoyed it. I hope you're better now with your integration. See you soon. Who's laughing now?